advanced stuff in policy gradient. Give me a second. Okay. So in last time we learned policy gradient. Let's recap the last time first. Last time we studied policy gradient, and then we derived this equation. But the problem is that it is very noisy, which means high variance because of this kind of reasons. So that we will learn some ways to fix noisy policy gradient. How can we decrease variance so that we can make it more stable? That is today's contents. And we will study 3 ways to fix policy gradient. First one is temporal structure, and second one is baseline, and the final one is bootstrapping. So this is from previous time. We derived why. So in previous time we derived the gradient of value function as the multiplication of probability, reward, and score function. And first one, temporal structure to fix noisy policy gradient. The reason why we introduce temporal structure is that we can eliminate noise from future actions that have no causal link to that reward. That is the core of the temporal structure. So we can eliminate future action that have no causal link to that reward. But there are some unnecessary terms in current policy gradient. So the previous one is, you can see this one, the gradient of expectation of reward. That is the gradient of value function, right? We can rewrite this one as the multiplication of expectation respect to the old trajectory and multiplication of reward and score function. And we can repeat same argument to write the gradient estimator for a single reward term. Instead of using R is a cumulative reward, right? There's a summation of all reward. Instead of focusing on the entire reward from all trajectory, we only focus on a single reward term at the time step t, which is denoted by RT prime, here RT prime. So R is the summation of, this is the R, right? This is the R. Summation of reward for all trajectory, all time step. So that instead of using cumulative reward, we can replace it with the single reward term, RT prime. And this one, as the trajectory spans from time step t equals to 0 to t minus 1. So that instead of t minus 1, we can use t prime, right? Because our focus is only up to t prime. What about actions? What about actions after t prime? Actually, we can ignore them. That is the core of temporal structure. Actually, we can instead of t prime, we can put large t minus 1, maybe. Instead of t prime, when we're summing the score function, instead of t prime, we can put large t minus 1. But actually, because of this one, causality constraint, current actions cannot affect past reward, right? That makes sense. Current actions cannot affect past reward. So we can ignore current actions when multiplying with the past reward. So for example, this one, ignore R0 log pi A 100 state 100. This is the reward at the time step t equals to 0, while the score function is from t equals to 100. This one becomes just 0, right? Expectation of this one is just 0. Because future action cannot affect past reward. Action at time step t equals to 100 cannot affect reward at time step t 0. So that instead of putting large t minus 1, we can ignore this, and then we can ignore ignore score functions where t is larger than t prime, and then we can just only focus on multiplication of score function up to t prime instead of large t minus 1. So that we can ignore many terms, right? We can ignore many terms. Instead of always using large t minus 1, we can use multiplication of score function up to t prime. That is the causality constraint. So that why this is good? Why this is good? So that we can reduce high variance. Because irrelevant noise removal, by focusing on the gradient for a single reward term t rt prime, we can eliminate the noise from future actions that have no causal link to that reward. We can eliminate noise from future actions that have no causal link to that reward. So how can we rewrite this one? How can we rewrite this policy gradient? So these are from previous slide. This is the same as the VES. And then expectation of respect to trajectory, where it's cumulative reward and multiplication score function. And then if we only focus on reward at single time step t prime, then we can rewrite this one. But how about this one? Let's revisit for all time step. This is for a single time step, t equals to t prime, where this one t equals to 0 to t minus 1. Based on this equation, we can expand this. Expand to t equals to 0 to large t minus 1. Right? So this is here is the first one. This is the same as the original one, just multiplying, so just cumulative reward for all time step. But instead of, why this happened? Sorry. So, okay. So instead of putting large t minus 1, which spans all trajectory, we only focus on t prime, right? That is and then this sigma is inside of this sigma, so that we can see like this one. This sigma is inside of this sigma. I mean, that's this sigma. Why this is an independent sigma, we can just put this sigma inside of this outer sigma. And then instead of putting large t minus 1, we can just say like a t prime. Because for t larger than t prime, that is just no meaning, right? No meaning. No meaning. Because the future actions cannot affect reward at the past time step, so that we can ignore all these terms, and then we can rewrite this one into this term, right? Instead of putting t minus 1, large t minus 1, which means summation of score function for all time step, we can just only focus on up to t prime. And then we can rewrite this one into this one. I mean, these are the same. This one and this one are just the same. You can just derive it with your hand. But the important thing is that we ignore score functions, future score functions, because future actions cannot affect reward at past time step. That is the philosophy of temporal structure. And then, so this is from previous slide. And then recall for a particular trajectory, tau, we call this one as the return, or denoted by GTI. We call this one as the return. Where this is from? From this one. Reward from where t prime is from t to large t minus 1. That is called return. So that we can rewrite gradient of value which means expectation of reward as the probability and multiplication of score function and return. And we sum them up, right? We can rewrite this one. This G is called return or reward to go. The sum of reward obtained starting from time t, not from time 0. That is important, not from time 0, until the end of the trajectory. And policy gradient with causality. Policy parameters are updated proportional to the score function, this one. That's true, right? Because, from this we derived delta theta in last time, right? So that the policy parameter, which are denoted by theta, updated by proportional to the score function, right? Proportional to score function. But this one is proportional to delta theta, and delta theta is proportional to score function. So that the policy parameter is theta updated proportional to the score function. And variance reduction significantly reduces noise in gradient estimation by discarding irrelevant past reward that the current action cannot influence. That is the philosophy of the temporal structure. To fix high variance, there are many useless terms, right? There were many useless terms. That makes noisy policy gradient a high variance policy gradient. So instead of using all terms, we can ignore many terms because future actions cannot affect past reward, or current actions cannot affect past reward. That is the basic philosophy of temporal structure. And an algorithm that used this kind of temporal structure, that introduced this kind of temporal structure, is actually introduced many times ago, 1992, which is called in capital reinforce. So instead of using O reward, it uses GT. Instead of RT, it uses GT to update theta here, right? Here. That is the contribution of this paper, which is called capital reinforce. Leverage likelihood ratio, score function, and temporal structure. Here, temporal structure. Delta theta t this is learning rate. This is score function, and this is return. So that we update parameter of policy network theta in proportion to the score function and return, right? An algorithm that firstly introduced this kind of return, which ignore many terms in policy gradient, so that it makes gradient very stable and relatively low variance, is called capital reinforce. It's not very complicated, right? Just based on our common sense, just future actions cannot affect past reward. Based on the common sense, we exclude many terms so that we make gradient quite stable and low variance, relatively low variance. An algorithm that introduced kind of idea is called capital reinforce, introduced in 1992 in Machine Learning Journal. And the second way to fix noisy policy gradient is called baseline. Let's recap this one. This is also from the previous time. The gradient of value function is the multiplication of probability, reward, and score function. And we're going to study baseline to fix noisy policy gradient. So these are objective of introducing a baseline, which is denoted by BS. You can see from this one is that B is a function. First, B is a function, and whose input is state. It looks like value function, right? Actually, it's very similar. Baseline is actually very similar to value function. It's a function, and it takes state as an input. So the first objective is variance reduction. Always, because as I introduced in previous time, the weakness of policy gradient is high variance. So that firstly, we introduce temporal structure to reduce high variance, and the second way, we use variance baseline to reduce variance of policy gradient. The primary goal is to lower the high variance of policy gradient estimator, leading to more stable and faster convergence here's the core idea of the baseline. Relative performance assessment. Shift the focus from absolute reward values to relative advantages, reinforcing actions only if they perform better than average expectation. You can see, we are not going to use absolute reward values. We are going to use relative advantage, reinforcing actions only if they perform better than average expectation. That is the core philosophy of baseline, introducing baseline. So the balanced gradient prevents the all positive reward problem, where every action probability increases regardless of its relative quality by centering the learning signal. Because, I mean, in some state, let's say you perform any action, any going right, going left, up and down, all action gives very high Q values. But this one, actually, it will lead to this kind of all positive reward problem. But that is not desirable, actually. So we actually, in baseline, we will compute some average reward for all actions, and then we can just shift to the relative advantage. Let's see details later. But anyway, this is the basic philosophy of introducing baseline in policy gradient. Instead of using absolute reward value, here we use absolute reward value here, right? Instead of absolute reward value, we are going to use relative one. As you can see here, reduce variance by introducing a baseline BS. So this is also the same as gradient of value, which is the expectation of reward, and then now this is a score function. In previous example, we didn't have this BS. In previous example, that was the end, right? But here we're going to introduce baseline. Okay, so that we are now using absolute reward. So that by subtracting this kind of average expectation, average reward, we subtract average reward so that we are focusing on relative assessment, relative evaluation of reward instead of using absolute reward directly. And there is some interesting mathematical properties that for any choice of B, you can choose B, anything. Gradient estimator is unbiased. You know, bias and variance. Let's see, this is the target. These are target. They are called, and then there are 4 cases here. There are 4 cases. This one, low bias, low variance. This one, low bias, high variance. This one, high bias, low variance, high bias, high variance. So variance, you know variance, right? In Gaussian distribution, we learn variance. I mean, that is like how samples are spreaded. And bias is how these samples are close to the target or average. So these one samples are, average of samples are close to target, right? So they have low bias or unbiased. But here it has high variance. But these ones, they are very far from target, so they have high bias. While this one has low variance, this one has high variance. Okay. And so here we have unbiased. For any choice of B, gradient estimator is unbiased. Their optimal choice is the expected return here, average of return. Interpretation is that increased log probability of action AT proportional to how much return are better than expected here. Originally, we only focused on increased log prob action proportional to how much return. That was this one. That was the previous one, just using temporal structure or just naive policy gradient, we were not talking about how much is better than expectation, how much is better than average. But here, by introducing baseline, we are trying to focus on how much returns are better than expected. Expected is just an average, right? By defining baseline, like average of expectation of reward, we can see this is the average, and then by subtracting this one, we are now see some relative assessment. So these are very long derivation, but conclusion is that expectation is 0. I mean here, conclusion is that let me first say the conclusion. So that here, conclusion is that no matter what BS you choose, it does not introduce bias. So that what this means is that according to policy gradient theorem, we learned this one in previous time, right? Delta J, delta value, is proportional to the multiplication of score function and return. And here, let's introduce B here. Then this one is the original direction. And here, as this one is 0, we somehow, with the long derivative derive, we learned that this one is 0, this one is 0. So that this one is 0. Yes, so that it doesn't matter. It doesn't matter. The gradient remains the same. That is the important thing. No matter which B baseline you choose, gradient is the same. Because this is 0. Why this is 0? Here's a proof why this is 0. That is the conclusion of this slide. Gradient remains the same regardless of which baseline you choose. Gradient is the same. Here, same direction. Since this one is 0, which is from previous slide, the overall gradient direction, which is expectation, remain identical to the original objective. And lower magnitude. Subtracting B centers the learning signal around 0, reducing the absolute magnitude of the update. And then this is the important one. So why we do this? Because it makes stable. It makes policy gradient stable. Smaller centered update means the policy doesn't overcorrect or swing widely, leading to much faster and more reliable convergence. So by introducing the baseline, we do not use absolute reward. We are now using relative reward, and then mathematically, it doesn't hurt anything. It doesn't hurt anything. Gradient remains the same, so it doesn't hurt anything. But so there is no bad thing. Just introducing baseline, gradient remains the same while making training more stable, so that in this way we can make policy gradient more stable. Then let's see this kind of derivation in more detail. So T is the current time step. So it tries to break up expectation at the past time and future and current one, right? And the BST belongs to only current one, so that we pull baseline terms out here, and then we remove some irrelevant variable here, right? And then this is the, I introduced this one in previous time, right? You can just write this one. And then we can cancel this, which becomes this one. And then we can pull gradient at the outside. But this one becomes 1, because the probability is always sum to 1, right? So that gradient of constant 1. The derivative of constant is 0. So that it becomes 0, and this becomes 0. So the expectation of multiplication of score function and baseline is 0. That is conclusion of this slide. And why this matter? Because, according to the policy gradient theorem, the gradient of value function can be expressed by expectation of multiplication of score function and return. If we introduce baseline, we can decompose this into two terms, right? These two terms. This is original direction, but here we show that this is 0. In previous slide, we show that this is 0. So that gradient remains the same. That is the conclusion of this slide. So by introducing baseline, we can all focus on relative assessment of reward instead of absolute reward, while there is no hurting at gradient side. There's no bad thing. It makes training much more stable by introducing baseline. And some preferred baseline, you can choose any baseline, but preferred one is just a expectation of all return, expected return. That is the preferred baseline, usually. So that we are now trying to introduce temporal structure and baseline in this algorithm, which is called vanilla policy gradient algorithm. Without temporal structure and baseline, policy gradient actually doesn't work well. So that we introduce temporal structure and baseline in the policy gradient algorithm, which is finally called vanilla policy gradient. Actually, it is not advanced. It is vanilla algorithm, unfortunately. So we initialize policy parameter theta and baseline B, and there's the iteration. Collect a set of trajectory by executing current policy. And each time step T is trajectory. We compute return. Return must be, we learned this one, right? We learned this in capital reinforced algorithm. Just cumulative sum of reward. But the important thing is that T prime start from T, not 0. That is the important thing and definition of return. And then we can calculate advantage. Maybe you are familiar with advantage. Have you heard of advantage? Have you heard of it? Can you remember? Advantage was the difference between Q and A, right? So that, no, wait. So this looks a little bit similar to value. Actually, it's true. It's very similar to value function. And we can interpret GTI as some kind of Q function. Let's see, summation of reward, right? So that we can, advantage is actually theoretical definition of difference between Q function and value function. But in practice, we can compute advantage in this way. That's the difference between GTI and BST. The return and baseline. And refit the baseline. What does this mean? By minimizing this one. It looks like minimizing. Minimizing means it looks like a loss function, right? And actually that's true. There's a function, right? It's function. B is a function, as I said. Then it takes ST as an input and outputs something. Then there should be some optimizable parameters inside of that function because it's like a function. So that we need to actually optimize parameters in baseline as well. And GTI, so that we encourage BST is same as the GTI. So there's actually two neural networks then. The first one is parameterized with theta police network. And the second one is BST. There are two neural networks. This is actually very similar to actor critic, which we will learn later. I'm not sure you remember, but in last time we learned that there are value-based RL, policy-based RL, and actor critic. Value-based RL, value, policy, and actor critic. Value-based RL, value, there is a value, but how about action? Action, it's like a triangle, implicit. Because we can just perform argmax at the estimated Q function, right? That is the value-based RL. And then from last time, we tried to shift from value-based RL to policy-based RL. How about policy-based RL? There is no value function, unfortunately. But here we have action directly from police network, from state, with output probability for all actions. That is the policy-based RL. Actor critic, there is a value and action. So that we use two neural networks in actor critic. The first one is it tries to estimate value function. Second one is police network. And this is a foundation of actor critic. We will learn actor critic later, detailed things later. But this is some kind of startup transition from police-based RL to actor critic. In police-based RL, there is only a single neural network. A police network tries to output probability of all possible actions from state. But here we have baseline, which is another network, so that we introduce additional neural network to estimate baseline, and it looks like actor critic, right? Although it belongs to policy gradient, it looks like actor critic. So it is start of transitioning from policy-based RL to actor critic RL. So here, when we introduce baseline, we have two neural networks, which still belongs to policy-based RL, but similar to actor critic. And then we update policy here, policy using a policy gradient estimate, G. Where is G? G is from last lecture. We know G, right? G looks like this. G hat. There's some of terms of score function and advantage, right? This is what we learned in previous time. We can plug in G hat into SGD or any optimizer. We can plug in the gradient so that we can derive the delta theta to update the policy parameter. So this is tries to update BS here. This one update B. This one update theta, right? So there are many words and maybe a little bit confusing, but I think this one can a little bit clarify your confusion. So far until DQN, we first focused on value-based RL with learnable value function, but actions are from implicitly obtained from estimated Q functions. We perform argmax, which is epsilon greedy approach, right? So to sample actions, to get actions from estimated Q function. But the value-based RL, the DQN, cannot be applicable to continuous action space. So we shift to policy-based RL, and then in previous time, we learned policy gradient, the foundation of policy gradient. And our goal was maximizing value function, but what we only have is policy gradient. Then how can we make our policy network in a way that we maximize the value function? That was the previous time's contest, right? And then we show that just simply using, gradient of value function is same as the proportional to the gradient of score function, so that we can use this G hat to update theta in policy network. That's the first transition from value-based RL to policy-based RL. And today we'll also start to transit from policy-based RL to actor critic. Because policy-based RL, there's no learnable value function. There's only a single neural network which takes state and outputs probability of all actions. That is called policy network. And then we just introduced baseline, right? So that it looks like value function, it's similar to value function. And then it takes a state, that means we need to estimate value function. So that we now introduce two networks actually. A network to estimate value function, value, and another network for policy network. That is called actor critic, which is widely used these days. We will learn this after midterm maybe. Anyway, this is a start of transition from policy-based RL to actor critic. Good? Any question? Good? So as I said, we have two neural networks. Modern policy gradient method typically maintain two separate functional approximators, often two distinct neural networks. The first one is policy networks, denoted by pi theta, learns the best action strategy to maximize returns. Second one is value network, denoted by V or B, learns to estimate the expected return of the current state, serving as a stable baseline. That is the birth of actor critic, as I said. From policy-based RL, we're now trying to shift to actor critic. This is the birth of actor critic. This structure is the fundamental precursor of the actor critic method, where the critic, which is called, can be baseline, evaluate the actor. And then, as I said, any baseline can be chosen. Any baseline can be chosen. We call Q for state action value. I think this is just recap. Anyway, you can choose any baseline. So that, but the preferred baseline is just preferred baseline is this one. That's the average of reward. So okay, so the basic philosophy is just we're trying to shift to relative assessment instead of absolute reward. And then that is the actually birth of actor critic. We are now using two neural networks when we introduce baseline. And the final one is bootstrapping. I guess most of you guys are not familiar with bootstrapping. So there are two things, bootstrapping and Monte Carlo. Let's see Monte Carlo first. Monte Carlo sampling is, I guess this might be included in statistics. The definition is a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. So this one shows visualization of Monte Carlo algorithm simulation for pi. Let's say we do not know any concept of pi. We do not know distribution of this kind of data. But we just randomly sample. We just randomly scatter all points on some space, and then based on this randomly scattered points, we are now trying to figure out real data distribution. That is the basic philosophy of Monte Carlo sampling. Core principle is it uses randomness to solve problems that might be deterministic in principle or too complex to solve analytically. As the number of random samples increases, the average of the result converges to the true expected value. That is the philosophy of Monte Carlo sampling. Why we're saying about the Monte Carlo? Because there's two things we need to know. The first one is Monte Carlo, introduced in previous slide. Second, temporal difference. I guess some of you guys are familiar with temporal difference. We learned this in previous time. So Monte Carlo, in our context, in this course context, what Monte Carlo means is that a method of estimating values by averaging the actual returns from multiple completed trajectories. So learning occurs only after, so a method estimating values actual return, here actual return, GT. What is the definition of GT return? T prime equals to T minus 1, RT prime. That was the definition of GT, right? Instead of using estimating one, actually, for example, in DQ network, you're not familiar with this one, right? We have seen this kind of equation lots of times when we study DQ network. DQ network, it uses estimated value, right? Instead of using all the reward actual returns, it uses estimated one. That is difference. Monte Carlo, it tried to use by averaging actual returns from multiple completed trajectories. Learning occurs only after reaching the terminal state. Relies strictly on real experience, but suffer from high variance due to cumulative noise. That is the philosophy of Monte Carlo in context of this course, RL. A temporal difference, or in other words, bootstrapping, a method that updates value estimate based on other learned estimate without waiting for the final outcome. That is called temporal difference or bootstrapping. Learning occurs online with every single time step t, because every time step t, what we can do is just we can immediately compute reward at time step t without taking care of a future time step, because future time step reward are from our estimator, right? The much more stable and efficient So we introduce bias during early learning phases. Why introduce bias? Because our model can produce garbage values at the initial training stage. So the estimated value functions might be totally wrong. So that it could introduce some bias during early learning phase, but it's much more efficient because we do not have to take care about all the actual returns. For this one, we need to in our environment, we need to actually compute actual return for all possible actions. That is very time consuming. There's a difference between Monte Carlo and temporal difference. So far, we used this one, right? In previous slide. We used GT, right? We used GT. AT is from GT, here AT from GT. So and GT is here, right? Summation of actual reward. So far, in policy-based gradient, in deep Q network we use this one, but in policy-based gradient we use Monte Carlo approach to get actual returns. But that makes inefficient. So instead of strictly relying on Monte Carlo, we're now trying to mix temporal difference. And we must choose between a noisy but truthful target, GT, and a stable but potentially lying target, bootstrapping. Because at early training phase, our model can produce garbage values, so that it might potentially produce lying target. The Monte Carlo, high variance, zero bias, safe but painfully slow to converge. Summation of true reward from state time step, right? So MC target is this one. GT is just a summation of reward from time step T to the end of the trajectory. The bootstrapping, low variance, high bias, fast and stable, but risking conversion to wrong solution if the approximation is poor. The summation of true reward of a single time step and function approximator. Here TD target is like this. It's very different, right? MC target and TD target. They are complementary. Low variance, high bias. High variance, zero bias. They are complementary relationship. Here, function approximation. Using a neural network to estimate values naturally introduces bias because neural network output could be totally wrong, especially in the early training phase. It's essential for handling large state space because it is much more efficient. So there's a dilemma. MC has high variance, zero bias, but painfully slow. Monte Carlo, bootstrapping, low variance, high bias. The estimated values could be totally wrong, but much more faster. Which one we need to choose? That is the dilemma. They have complementary relationship. But so far, we have only relied on Monte Carlo MC, but it is too slow, so that we are now trying to mix bootstrapping in our policy gradient algorithm. Actor critic, I introduced this briefly, right? We will learn actor critic detail later. Maintain explicit implementation policy and value functions, I said. And policy gradient formula with value function, these are from previous slide, right? This is absolute reward, and then we introduce the baseline, and letting the baseline be estimate of the value. We can represent gradient in terms of state action advantage function here, right? We can just define this advantage function. The advantage function is defined like this. So we are now trying to change from this one to this one. So what becomes difference? So from return to estimate here, this is GT, right? GT. Summation of actual returns. This is summation of actual returns. But here, Q is estimated one. This is actual. This is estimate. Right? This one is what we learned so far. In policy gradient, we use GT based on actual gradient, actual reward, we have studied holistic gradient, but we are now trying to shift from actual reward to estimated one to make it efficient. So we shift from this one to this one, where A is a Q minus V, right? So instead of using actual reward, we use estimated reward. It's a little bit similar to deep Q network, right? So from returns to estimate, transitioning from empirical returns, GT, to learned value function, QMV. This is the actor-critic foundation. By replacing the raw return with the learned Q function, we move into actor-critic framework. Besides actor-critic, we use two networks. And generalized advantage, expressing the gradient in terms of A advantage allows for more flexible and stable update using bootstrapping. That is the philosophy of using bootstrapping instead of Monte Carlo. Well, as I said, we have complementary relationship between Monte Carlo and bootstrapping. Monte Carlo, zero bias but high variance. Bootstrapping, low variance but high bias. So that we can mix them, and then there can be many possible designs. For example, here, it strongly relies on bootstrapping, right? But how about this one? This one slightly increase the proportion of MC, right? But this one, totally MC. So there's a bootstrapping, MC. There can be many possible design choices between them. So you need to make a sweet spot between them, make a balance between them. Bootstrapping and Monte Carlo, there is a, between them, there can be many possible design choices. If you rely too much on bootstrapping, then your network might suffer from high bias. High bias, low variance. This is zero bias, high variance, right? You need to make a sweet spot between them. If subtract baseline from above, it get advantage estimator. You can just subtract the baseline. The important thing is that how can we design reward? How many actual reward we are going to use? That makes your training. If you use many actual reward, then it makes training slow, but suffer from high variance, but zero bias, right? So let's check your attendance. Check your understanding. So that all that are true. Can you guess which ones are true? Let's try 2 minutes. I will give you 2 minutes. This is the first one, second, third, and fourth. Anybody? First one is true. First one true. First one true. And second one true. Third one, last one. So some of you guys say first and last one, and some of you guys say only fourth. So let's see. This one is low variance, low bias. Low variance, low bias. That is perfect, right? Low variance, low bias. That is perfect. We do not have to consider this one. We always need to consider this one, right? Low variance, low bias is perfect. But unfortunately, this one suffers from high bias, unfortunately, because this one, estimated one, could be totally wrong at the early of the training phase. So low variance, low bias, it is perfect, but unfortunately this one it has suffered from, so AT1, it has high bias, low variance. So it's false actually. Second one, it's the same, right? It suffers from high bias. Third one, AT infinite. Low is low bias, high variance, right? Low bias, high variance. So only this one is true. Many things are false. Good. This is just the same as the previous one. So temporal structure, baseline, and then integrating the bootstrapping, so that instead of using actual return, we use estimated advantage when computing G hat. And then we can just plug in G hat into SGD or any optimizer to update data. So this is a summary of poly-space RL. In previous time and today we study poly-space RL. It has good point and bad point, of course. Good point is that better convert properties, effective high-dimensional continuous action space. Definitely true, because deep network assumes the non-infinite number of, finite number of action, and can learn stochastic policies, of course. Disadvantage is that typically converts to local rather than global optimum. And evaluating policy can be inefficient, high variance, as we learned. GT suffer from this one, right? Though baseline temporal structure helps. And then, so value-based RL, policy-based RL, combining together, that becomes actor critic. We will learn, I'm not sure, next time or anyway, we'll learn this later. So this is the end of today, and any questions?